Hey everyone, welcome back. This video is covering your fourth lab assignment in SPSS, and I wanted to note that it's due October 25th, which may seem like a little bit of a ways away, but that's just because this coming Saturday, your background and reference section are due for your research project, and then the following week, I believe your second exam is due. So that's why, if it seems like there's a little bit more time to complete this, there's just other stuff going on in the course before then. So this assignment, describing qualitative and quantitative variables, I have uploaded a data set. It's just called Lab 4. You can access it here in the assignment details. In the SPSS book, we are in Unit 5, and this is Lesson 20 and Lesson 21. For Lesson 20 especially, some of this might seem a little familiar, especially the bar and pie chart, because we did that in the third lab assignment. But I did want to show you guys that sometimes in SPSS there are a few different paths to get to the same quote-unquote answer or output, like creating a bar chart or a pie chart. So I wanted to be able to show you that there is a little bit of variety. So if you forget one way, maybe you'll remember a different way. Or maybe one just makes more sense to you, or you like it more. To each their own. But for our first step, we want to get frequency tables for gender, ethnicity, and job type. So going to our data set, for this one, I wanted to show you guys that we have our usual ID variable, gender, we have a variable for ethnicity, job, high school GPA, and college GPA. For this, you will notice that, for the first time, we're dealing with categorical variables that are not recoded as numerical values. And I wanted to show you this because it is possible when you're doing your charts or, early descriptive statistics to keep these categories as what we call in SPSS string text. So string just refers to like text words, non-numerical values. So when you're doing these charts and just frequencies, early descriptives, you can keep the string text. SPSS will read them as categories for these variables. But if you're doing any other sort of analyses like t-test, ANOVA, anything like that, you do need to have these recoded into numerical values. So that's typically why I encourage you to recode them. That's why we've been practicing. But I just wanted to show you that it is possible to, build some of these charts and tables with string text. So starting off, we want a frequency table for these three variables. So where do we go? We'll go to Analyze, Descriptives, Descriptives, and then Frequencies. So I'm going to reset this. So typically when you pull it up for the first time, it'll look like this. But we're just going to move our gender, ethnicity, and job variables over. So if you right click, you can move them all over at once, or you can do it one by one, whichever. You want to be sure that this display frequency tables is checked. We can also come through here and pick out different things. But for now, what we're doing for this assignment, what's already pre-selected or not selected is totally fine. As a reminder, you can also paste what you're doing into the syntax. See if my syntax window will come up. Oh, there we go. I think I pasted it twice. So one reason you might do this is especially when you're working with a lot of different data sets, you need to run these same analyses or just the same syntax in these different data sets, and you don't want to take the time to actually click through that. You can just open up a syntax file with the syntax as long as the variables are, either the same or edited to reflect the current data set. Sometimes it's really nice to just have that syntax saved so you can just hit run, substitute those variable names that you need to, but you hit run and all your output is there very quick. Again, this is most useful when you're dealing with like large data sets, repeated analyses, things like that. But just wanted to show you that. We don't need to do that today. So going back to analyze, descriptive, and then frequencies. So I have everything I need here. Display frequency tables is checked. I'm going to hit OK. So now when I come to my output, I have my frequency tables for gender, ethnicity, and job type. The most useful thing, especially for categorical variables, is typically going to be this percent column. So percent, frequency is giving you the count of cases or participants in that data set that are in that category. And you know, this is useful too, but usually when presenting, especially when you get into higher sample sizes, the most useful thing is percent, because you're typically more interested in the distribution of your sample than the exact number. So when you're presenting to an audience, 58 people out of 1,000 doesn't mean a lot. But obviously 58 when the sample is close to 120, is a little bit more interpretable, like just by looking at it. But just in general, you're typically interested in the gender distribution, not like the exact count, if that makes sense. So percent tends to be the most useful when you're looking at distribution across the sample for categorical variables. So how evenly distributed are my ethnic groups, gender, and job types. And this is really important. It doesn't always, when you're recruiting for a study or trying to balance your sample, you're not going to get a perfect balance, especially with things like job type, unless you're specifically like targeting recruitment for these different job types very strategically, but it still doesn't say how many people from these different jobs are then going to participate in your study. So you can recruit in a balanced manner all you want, but it doesn't necessarily decide who ends up in your data set, if that makes sense. So a perfect balance is usually not expected, or obviously it's encouraged to get as balanced as possible, especially with things like gender and ethnicity, depending on what you're studying. Those can be very important variables to have some balance in, especially when you're trying to make, when you're trying to generalize your findings. That's when the balanced distribution means the most, because it's like, okay, you're trying to generalize these findings. Did you actually have a sample size that was balanced enough to say you got enough information from these different groups to say it generalizes to that group? So hopefully that makes sense. But yeah, percent tends to be the most useful when we're dealing with categories. But yeah, we have everything we need here. So moving on to our next step, we want to create a bar chart for our job category frequencies. Okay, so last time we learned how to do this using graphs and chart builder, but I want to show you that it is also possible to go to analyze, descriptive statistics, frequencies. Can reset this. I'm going to move job over, and instead of clicking just OK, I'm going to come to charts, and I'm going to select bar chart. And for the last one, we wanted frequencies and percentages, but for this part of the assignment, it said we specifically want the frequencies on this bar chart. So OK, or continue, and then OK. And now we have a bar chart with our different job types represented. So very similar to what we did before with the different school clubs. We just have a lot more categories down here. But now you know that there's a different way using the descriptive statistics and frequencies to get this information. Moving on to the next part of the assignment is a pie chart for ethnicity. So again, last time I showed you how to build a pie chart using the chart builder. And this is a very similar way to go about things, but under graphs. And then instead of chart builder, we're going to go to legacy dialogues and select pie. And when this pops up, my default is summaries for groups of cases, and we want to keep that. basically that just means we're getting, again, for the different categorical groups, we're getting summaries for those. So that's the one we're interested in. And then we can move ethnicity over to define slices by. And under slices represent, we can keep this as n of cases. So then hit OK. So now we have a pie chart representing visually the ethnicity distribution within our sample. And something I want you guys to do is add data labels to each slice of these. So this is listed in the assignment that you need to add data labels. I am not going to show you how to do this time because I showed you how to do it last time. So this is one of those things that I've already shown you how to do. We did it with a bar chart, but it's very similar. So this is going to be something you do on your own. Okay, so for the next part of the assignment, this is also something you're going to do on your own. I'm going to show you how to insert text into your output, but that's it, because the rest of it, I want in your own words for you to summarize the distribution of gender, ethnicity, and jobs. So basically what I want you to do is I want you to look at, both bar chart, pie chart, and the frequency tables, and I just want you to, write a few sentences about things you're noticing. Is it evenly distributed among each category? Is there one that is appearing more than the other, especially with job type? Is there a category that's better represented, not as well represented? So what are some things you notice when you look at these frequency tables and charts? So what you're going to do in order to do that is you can come down, I'll just click on this, maybe last part, and then I'm going to come up to insert and new text. And so you see below where I just selected, now I can write text. I can't type today. Gender distribution, whatever. So I'm not giving you what to write because I want to hear your own thoughts. So take some time to just, again, review these tables and charts and just think about what is going on with these, what is going on with our data. So how is our data characterized, by what types of jobs, our, again, ethnic group distribution, our gender distribution, any of your own thoughts there. And since we're all dealing with the same data, I can't give you what to say because then all of the notes that I read will be exactly the same. So I want to hear from you guys. So that is lesson 20. Our next part of the assignment, moving on to lesson 21. So this one, we want descriptive statistics for high school GPA and college GPA. And when I say that, I'm giving you the exact descriptives I want, which refer to mean, standard deviation, minimum, maximum, skewness, and kurtosis. Okay, so coming here. So we're going to go to Analyze, Descriptives. This time, we're moving our variables over, going to Options. And this is where you're going to make sure that everything that I mentioned in the assignment that you should have is checked off. So we have mean, standard deviation, minimum, and maximum values already checked off. We just need to check skewness and kurtosis. So hit continue, and then OK. So now we have a descriptive table with all the information I requested on those two variables. And in case you're curious, skewness, or maybe you just need a refresh from your stats class, but skewness and kurtosis are how we help characterize and kind of verify that our data is normally distributed. So again, going back to the normal distribution or bell curve, inverted U shape, which I'm sure you've heard a lot, especially from your stats class previously, but skewness sounds, more what we would assume, basically how the data is skewed. So, you can have no skew in the data, and that would be like symmetrical. So skewness is really getting at the symmetry of the data. So you can have a skew in one direction or the other, and that's when we get those kind of like long tails in our bell curve, where if you kind of cut off the tail, you would get what looked more like a normal distribution, but with the tail it looks highly skewed one way or the other, because of usually some outliers or extreme values in the data. And then kurtosis is not as intuitive, but it is also just one of those things we use to characterize our normal distribution. So high kurtosis would be basically a higher peak for that like bell curve, so the middle of the data. So more a steeper or like very high, like a much higher peak, and you get really fat tails on either end. Whereas low kurtosis, you're going to see maybe more of a flatter peak. So maybe instead of an inverted U or bell curve, it just looks like a little hill. And then you get really thin tails really close to the, axis. So kurtosis doesn't really have to do with it being skewed in one way or the other. It's more the characteristics of how high the peak is and the characteristics of the tails. Okay, for our next part of the assignment, we need to create a histogram with college GPA specifically. So here, this is another example of where you can go to two different places. So you can go to Analyze, Descriptive Statistics, Frequencies, and then we can move college GPA over and go to Charts, Histograms, and based on the assignment, we want to make sure this is checked. So Show Normal Curve on Histogram. So we can hit Continue and OK. So it not only gives us a frequency table, which we don't need for a quantitative variable like that. Like we don't want to see every instance that a certain value appears. So another thing we can do is go to Graphs, Legacy Dialog, down here to Histogram, and move our variable of interest over, and then just make sure this is checked. And then we can hit OK. So we got the same thing. We just skipped over getting that bulky frequency table that we just don't really need for a variable like this. So here we have our histogram. And again, it's showing that normal curve. So maybe some of what I was saying about skewness and kurtosis will make a little bit more sense. As you can imagine, high kurtosis would have like a really high peak and fat tails because they would maybe the peak would come up here and the tails would come way up here, leaving a lot of room between the line and the axis. Whereas a low kurtosis, maybe the peak would be like down here, just to show something very extreme. So you have a really low peak that then comes down and has really thin tails. But anyways, basically it just helps us understand the shape of our normal curve with a given data set. So we have our histogram. So next we want to get a stem and leaf plot for our high school GPA variable. So here we can go to Analyze, Descriptive Statistics, and Explore. So we want to move the variable of interest into the dependent list. Go to Plots, Stem and Leaf, and everything else we can leave as is and hit Continue, then OK. So now we have our box plot of high school GPA. So something to note here is that this is the actual stem and leaf plot right here. This is actually a box plot, which is just SPSS gives that for us, which is a nice visual representation. But the actual stem and leaf plot is right here. And what that refers to is it just basically breaks down the frequency that these values come up in our data, broken up by like the leading number, so the first digit. So sometimes visually, especially with smaller data sets, this can be helpful, so you can kind of see like, oh, the, you know, how many times like a GPA starting with 1 occurs versus 2, 3, and 4. But then we get this nice visual representation with the box plot where we can see our minimum and maximum value really easily, so ranging from 1.0 to 4.0. But, the center of our data, the middle like portion of our data is represented by the actual box. And then that's when you can get into the different quartiles and stuff like that, like the middle quartile, and stuff like that. But for this, as long as you have this here, but SPSS, like it did with me, will likely just give you the box plot along with it. But this is what you need for the stem and leaf plot. I just want to be sure you guys know that this is the actual stem and leaf, and this is a box plot, but both are produced by SPSS. So moving on to the next part of the assignment is an actual box plot. So we want to create a box plot comparing college GPA distributions for men and women. So we're using our gender variable and our college GPA variable. So what we can do is going to go to graphs, then legacy dialogues, and box plot. And we want to keep it simple as the option we check, and summaries for groups of cases again, because we're interested in those categorical variables. So our category axis is going to be gender. And college GPA goes under our variable box. And I don't believe you need to check anything here. Yeah, this is mainly how to deal with like missing values, which we're not dealing with in this data set. So, okay. So now we have a box plot for both men and women showing the distribution of college GPA values. Something to note here that I think is kind of interesting, not necessary for the assignment, but we can see like the minimum and maximum values are pretty close to being similar, but for some reason, we have this outlier identified here separate from the box plot, but we don't have that for women. And just looking at this as like a thought exercise, feel free to pause if you want to try and answer yourself as to why that might happen. And we can even see that our like middle center of the data is really close to one another, with, maybe women being a little lower, but that's not necessarily statistically significant or anything, but we can just see just by visually looking at the data, it's very similar. But something else we can see is that, the actual box is a little bit different for the two categories, men and women. And what I would suggest is probably happening here, I haven't, actually run anything to look at the data, but just what I'm visualizing here, is that it seems that while the center or middle of the data is similar for both groups, men and women, it seems that men are more, the data is more tightly concentrated around the center. So there's less what we call spread. Women, we can see, and spread, is exactly what it sounds like, how spread out is the data. So it was probably, this score was probably identified as an outlier, even if the maximum value is close to women's maximum value. But here it's just identified as more of an outlier, and that's just because we're seeing, in this data set, we're seeing data with less spread, so it's more tightly concentrated around the middle or mean of the data, which means that this value is probably enough standard deviations away that SPSS is like, this is an outlier. Whereas for this category, it's possible that while the middle of the data and the minimum and maximum are very similar to men in this data set, it seems like there's just more spread. So the data is not as tightly concentrated around the mean or middle of the data, meaning you have more variability in your scores in maybe the more like tail area or just getting outside of the middle of the data. So if you were looking at the normal curve, you would see a lot more spread and it less tightly concentrated around the mean. Versus over here, it just seems like, again, some of the key descriptives here are going to be similar, but the other data is falling more tightly around the mean. So that's kind of how I would conceptualize it. Basically, how tight the data is aggregating around the center or middle of the data, so the middle data point. And I don't mean like the literal middle when I say that, as in, okay, the minimum is, say, 0 and the max is 4, so the middle is 2. I mean, in this, for men, the middle of the data is somewhere between 2.5 and 3.0. Similar for women. So the middle of the data for these different categories is very similar, but again, how tightly the data is aggregated around that center measurement, so the mean or median, is going to differ between these two groups. So yeah, I like to think of it as like spread and kind of tightness around that like center metric, whatever your measure of center is. All right, moving on to the last part of the assignment, percentile ranks. This will likely be the hardest part of the assignment, but it's not worth a lot of points actually. So each step is worth, 1.5 points. Each like major portion of this percentile ranks is worth 1.5 points. So it's not detrimental to you if you don't get this, but if you follow along with me, you should be just fine. So the first thing we want to do, so we have computed a rank variable before. So we've talked about attributing this rank in the data. So basically like where they fall, how to translate their scores into a general rank. So it's like, okay, we can interpret this as like on par with average of our main GPA, or above average, below average, all of that. But what if we just want a rank and then on top of that percentile rank? So first, without assuming normality. So the reason this is important, so we're going to be working with college GPA. So we plotted that on a histogram here, and we showed the normal curve. And I'm not going to interpret anything related to whether I think this is meeting normality or not, because that's also the last step in the assignment, is for you to say which method you think is appropriate. Should we approach this without assuming normality or assuming normality? So I am not saying anything else in regards to that, but just letting you know we did plot this, and there is, a reference for you to look at and, interpret and decide which method you think is best. But we're doing both methods for the sake of showing you how to do that. So first, we're going to compute these percentile ranks without assuming normality. So say we can't verify that our data is meeting a normal distribution. So maybe there's some asymmetry or whatever it may be, but we say it's not normally distributed. So we need to approach this with computing percentile ranks without assuming normality. So in that case, we need to use our raw scores. So basically, the scores that we have in here for GPA, we need to use like the current scale it's on, raw scores. So what we're going to do is go to transform, rank cases, move college GPA over, rank types, make sure rank is checked, ties. So I don't think I've showed this before, but this is basically just defining how to SPSS how they deal with ties. So basically like duplicate scores, recurring scores. So here I'm going to put it as high. So basically rank assigned to ties is basically the highest possible score that they could get. I think last time we used mean, and that's why we got those like 0.5 values, What this means is that both or all recurring scores will get the highest rank possible. And I did this last time as well. Assign rank 1 as in spot number 1 or first place, whatever you want to think of it as, to the largest value. Because in this case, when we're dealing with GPA, the higher values are associated with, the quote-unquote better GPA. Smallest value, could be used in cases like time, like if you're running a marathon, like your, what's it called? Okay, I can't think of it. But your pace, that's what I'm trying to think of. Sorry, totally buffered for a second. But maybe you want to use your pace. And in that case, the smaller values would be considered like, first place, top ranking. Okay, so we're going to hit OK. And now here we are, we have our rank variable. However, this itself is not enough. So this is where we stopped last time. And you can see we have, different ranks than we've seen before. And that's just because we have, 120 in our sample. So we have more people. So that's more ranking spots, if that makes sense. So we have our rank variable, but we need a percentile rank variable. And what we're going to do is transform compute variable, and we're going to name this percentile rank. I always like to do this, use expression as label, so you can see the formula that was used to calculate the new variable. And I have this formula here, but essentially what you need to do is, like I just copy and pasted, but you need to move your rank variable over, then divide it by the sample size, which is 120, times 100, and that is going to give you your percentile rank. Okay? So we have now done the first step. So we have percentile ranks without assuming normality. Now, the second method, which is assuming normality, so if your data is normally distributed, then you can use what we call standardized or z-scores. And there's different instances, different situations, but the short answer of why z-scores or standardized scores are desirable, or why would we even use them if we can do it this way, like who cares, right? And I totally get it. So we have those, and that's great. But one thing is sometimes we're looking to standardize the scale points that it's on. So, 1.0 to 4.0, not the most easily interpretable in terms of the different variation in scale points. So like small differences mean less to us. So maybe we want to standardize like the scale that it's on is one example. So how to do that? We are going to go to Analyze, Descriptives again. We're going to reset this. I'm going to move college GPA over. And this time we want to save standardized values. So make sure this box is checked. We don't need any of the actual output. We're really just interested in the standardized values. You hit OK. And now you'll notice we have a new variable created, which is the z-score for our college GPA. So basically it takes our college GPA variable and standardizes the scores. Okay, so now we have our standardized scores. And all this means, I know it sounds intimidating, why not just use the raw scores? But all this means is, when you think about standardized scores, it's basically, converting these scores in retrospect to the mean and how many standard deviations away from the mean is that score. So with standardized z-scores, your mean is always 0. So 0 indicates your mean in the data. And then you get negative and positive values, but it's typically around, -2 to +2. but it can be -3 to +3. But the big chunk of the data is going to lie within 2 standard deviations of the mean in either direction. But then you'll get to the more like outward tails, and maybe more outliers, or potential outliers, I should say. And you can get up to 3 standard deviations, which is why you see, values of 2 and some change. I'm not seeing any right now. Hold on. I'm trying to find you an example. So like 2.6. So that's not within 2 standard deviations of the mean. It's really technically within 3 standard deviations, which we know 95% of the data is occurring when it's normally distributed. Again, going back to that normal distribution, 95% of the data is going to be within those 3 standard deviations. But again, even more of the data is within, like the largest chunk of the data is within like the center. So you're not going to see as many of these like higher values. So the positive value means that this person's college GPA is 2.6 standard deviations above the mean, which just means a very high GPA, basically, if you want to interpret it that way, a very well above average score. What's cool about using our standardized scores is that, for the raw scores, we had to do both rank and percentile rank. When you have the standardized scores, you actually don't have to do both steps. There is a formula you can use to get straight to percentile rank, which is really cool. And again, that goes back to this being on a standardized scale rather than the raw data points. So you don't have to first compute the rank to get percentile rank. You can just go from the z-scores to percentile rank. And how you do that is with a formula. So you're going to go to transform, compute, and you can name this, z per rank, just so you know it's different from your other per rank or percentile rank. And I have a formula that you're going to use. So CDF.normal in parentheses is the variable name, which is your z-scores of college GPA, comma 0, comma 1, close parentheses, times 100. So what is this formula? So CDF stands for cumulative distribution function, which I have to slow down to say because it's hard to get it right. And then we're defining it as normal. But essentially what we're doing with this formula is just assessing each data point to see, there's different ways I can explain this, but I think the quickest and simplest way for this class is to assess area under the curve. So when we go back to that normal distribution, the normal bell curve, basically when you pick a certain point on that x-axis, so say it's 0, which would be the mean, how much of the data falls under that point, at or under that point. And so essentially what this is measuring is it's giving you a probability. So the probability that another data point falls under this point we're defining, say 0, which would be 0.5, because half of the data exists below the mean, whereas the other half of the data exists above it. But essentially this gives us our percentile rank when the scores are standardized. So again, if a score is 0, it would get a rank of 0.5, 50th percentile. Hopefully that makes sense. But essentially, you're just going to use this formula. Maybe you've learned about it before, maybe you haven't. Just understand that you don't need to know the specifics of what this formula is calculating. You just need to know how to use this formula to get your percentile rank using z-scores in SPSS. So I gave you a little breakdown, but it's really not necessary for you to know all of that. I just want to try and contextualize why we're using this. So it is calculating area under the curve of a certain point. So it's taking each, because remember, we're going to get a new variable. So each case or participant is going to have a new value, which represents their percentile rank based on z-scores. percentile rank when assuming normality. So each z-score is going to be assessed to look at, okay, what is the probability that like another data point falls at or below this? And that basically represents area under the curve when you're looking at a normal bell curve. But for the purpose of this class, what it does for us is compute percentile rank based on standardized z-scores. So once you have this formula in, again, CDF dot normal parentheses, open parentheses, z college data, so your z-scores of college GPA, comma, mean, which is 0, so that's what this 0 is representing. You're defining the mean. 1 represents standard deviation. Times 100. So close parentheses times 100, and that gives you your percentile. So you're going to hit OK. So now we have a new percentile rank variable here. And if you're interested, you should be interested because it's part of the assignment. Something you'll want to look at is just comparing percent rank using the raw scores. So this is when we use the just raw data from college GPA versus the percent rank based on z-scores. And you'll see they're not far off, right? So they're, close-ish. So not too far off. At this point, we have our new variable for our percentile rank based on z-scores. But one problem is, the rest of our assignment has all been verifiable through our output. And I only want you to submit one file, that is your SPV file containing, if I can find it. Everything else has been verifiable. We were creating charts, getting frequency tables, some descriptives. But now we just need to run one more frequency little here. I'm going to reset this just so I can see that you successfully did this. So you're going to move over your rank of college GPA. So this was rank using your raw college GPA scores. You're going to move over your percentile rank using raw scores. And then finally, your Z percentile rank score. So I don't need Z scores because if you have this last one in, I can verify that you did, the Z score part. And you just want to make sure this is still checked, display frequency tables, and hit OK. So with this, I will be able to verify that you did the percentile ranks correctly and just using your output file. So you don't have to upload multiple files, although I still recommend that you save this data file. Just by chance, if you learn you did something wrong later and you want to come back to it so you don't have to redo this work, just save an updated version of Lab 4, which I'm going to do right now. So before you submit your assignment, I want you, I told you to take a look at, the different percentile rank variables. Just note, okay, they're kind of similar. I, mentioned that we have the histogram of college GPA already, so we can see how it stacks up compared to that normal curve that we plotted on the histogram. So that box we checked that said show normal curve. So I want you to look at those and consider what we've talked about. And I just want you to add another note. So if you remember, you were supposed to add a note talking about the distribution of these different variables, these different categories in the data. So you should add a note just talking about things you noticed. And finally, you're going to add a note at the end here. So again, you can just come to this last box, hit insert and new text. And then I want you to add a note where you discuss which method seems more appropriate. So, is our percentile rank without assuming normality, or the one where we did assume normality, so we use these scores? Which one is more appropriate in this case? Give some justification as to why. So after you add that note about which method, seems more appropriate based on the histogram we created of college data, the college GPA data, then you're done. So you'll submit your output file. Again, just one file. So all of that should be in the same output file that we just did. You don't need to create separate files. I've also come up with a suggestion for your file names. So I noticed a lot of, different ways that people tend to name files, which totally makes sense. But I think a good kind of best practice, especially when you're in undergrad, is to use your last name, first name, the course, and then whatever assignment it is. That is not only easiest, when I was an undergrad, that is how I track down different files, but also, your professors and TAs will really appreciate it because it's a lot easier to tell after I download your submissions whose is whose. I'm downloading, a lot of submissions at once. So Lab 4 output means nothing to me in terms of who you are. Obviously, I can track down who it is, but I just want you to know, for the sake of both professionalism and for personal tracking of files, this is a really good practice. And if you find out that there's a different format you prefer, that's totally fine. It's just keeping this essential information in there, like your last name, first name, what course it's for, and then what assignment it is. So if you prefer some variation of that, totally understand. But just letting you know that, a very simple and clean way to make sure that your file does not get lost among other files, both when you're going through your own stuff, say you name something Lab 4 and then you're in another class that has a lab and there is a fourth lab assignment and you name it Lab 4. So both for yourself and for your professors and TAs, it just tends to be highly recommended to name them this way. So that's my little soapbox for this lab video. And so it's due October 25th. I have office hours, as always, Tuesdays and Thursdays from 4 to 5 p.m. I hold them virtually. So my Zoom link is always in the syllabus, so I don't send it out each week or anything. It's just always there for you to find. But yeah, please reach out if you have any questions. I'm sure there'll be questions about other assignments between now and then, but I'm here to help. And good luck.